Okay, welcome to November. We're one lecture away and then we have a reading week. So that's pretty exciting. And hopefully reading week won't be too terrible. And yeah, I was going to try and bring leftover Halloween candy, but I got cleaned out last night, so that's unfortunate. So I actually got cleaned out by like 7:30. But today we're going to be talking about more page replacement and the clock algorithm, which was kind of that approximation of least recently used, except we're actually going to be able to implement it. So here's the algorithm in all its glory, and the rest of the class we're just going to go over examples again and again. So it's the data structures it just has a circular buffer of pages. So it keeps a circular list of pages in memory or buffer, and it just uses one bit to keep track of whether or not it is referenced. So every page just has one bit associated with it, whether or not it has been referenced somewhat recently. And whenever I show the algorithm, I'm going to put the reference bit in the light gray box. So the light gray box will either be 0 or 1. So then the other thing it has a circular buffer, and each page has a reference bit, and then the final part of it is there's an iterator, which you can think of just as the clock hand. So it just essentially just has an iterator pointing to the last element examined, which would be a page. So then the algorithm works like this. So if you need to insert a new page, if I need to swap a new page into memory, then I check the hand's reference bit. If that page is currently a 0, then I delete it and I swap in that page. If it is not a 0, which means it's a 1, then I just change its reference bit from a 1 to a 0 and then advance the iterator one position. And then I just keep going on like this until eventually I find a place for it. So that's all it does. And whenever you reference a page, whenever you access it, it's just going to set the reference bit to 1, which keeps track whether or not it's used. So it's better than actually doing all those pointer updates. All we have to do is write a single bit every time we do a page access, which is more realistic to do. So that's it. And whenever you insert a new page, you would advance the hand after you place it, essentially to keep that page, make sure it doesn't get its reference bit set to 0 whenever the next thing comes in. So you want to advance the hand after you swap in that page. So this is what it's going to look like. So this is our question. So we're going to assume, again, physical memory can only hold 4 pages, and then we have the following accesses: 1, 2, 3, 4, 5, 2, 3, 1, 2, 3. And again, we're always going to assume that all pages are initially on disk. So in this example, this is what our clock would look like. So we have 4 positions, and it's a circular buffer. So each one is going to point around the clock, and you can draw it in a nice little circle so it actually looks like a clock, and the whole thing makes sense. And then all the reference bits are 0, and there are no pages loaded in. So we'll just say in the white box that there's no page there, so we'll just give it a 0. And then all the reference bits are 0 because they're in the light gray box. So now we just follow the algorithm from the last slide. So if we access page 1, we have to swap it in. Our current hand on the clock points to a location where the reference bit is 0, so we get to replace it. So we would swap in 1, set its reference bit to 1, and advance the iterator of the clock. So this is what the clock would look like right after we access the first page. So now it is in memory. Everyone good so far? So same thing's going to happen when we access page 2. It's pointing at a spot where the reference bit is 0, so we're going to insert it, put the reference bit as 1, and advance the iterator one spot. So this is now our clock. After the second access, it is now in memory. So in memory, we now have pages 1, 2, and then both the reference bits are 1. So this is going to look a little boring. So page 3 comes in. We're pointing at something with a reference bit of 0. So we would insert that. And now we have page 4. So same thing happens. It would have a reference bit set as 1, and we advance the clock. So now when we access page 5, then a lot of really boring stuff is going to happen. So now we have to follow the algorithm like it said before. So if it's pointing at something where the reference bit is a 1, we can't get rid of it because we're trying to approximate least recently used. So we're going to essentially give it another shot at life. So when we first access page 5, we're pointing at something where the reference bit is 1. So we're going to change it from 1 to 0 and then advance the iterator. So we would do that. Now we're pointing at something else where the reference bit is 1. So we would advance it again, set it to 0. Now again, we're pointing at another page where the reference bit is 1, set it to 0, advance it again. And then we're going to do it again. So now we're pointing at another location where the reference bit is 1. We'd set it to 0, and we'd advance the hand. Now, at this point, it's pointing at a location where the reference bit is 0, so we can replace it. So we would replace page 1. We would swap it out with page 5, set its reference bit as 0, and then advance the hand. So our clock would look like this right after our access to page 5. So now we would access page 2. So right now its reference bit is 0, but we just used it, so we should update its reference bit to indicate, hey, we're actually using this recently. So from the access in 2, instead of like FIFO where it did nothing, we would update the reference bit to a 1. And then our next access is to page 3. So again, with page 3, currently its reference bit is 1, and its reference bit is 0, and we just referenced it, so we should change its reference bit to 1. So now after the access to 3, it would look like this. And again, on references, we're just trying to do the minimum possible, so that's why we don't touch the hand at all or do anything with that. We just set a bit if it's not already set. So now, when we access page 1, now something more interesting is going to happen. So if we access page 1, well, currently the iterator is pointing at page 2. Its reference bit is 1, so we can't kick it out, but we can change the reference bit from a 1 to a 0, advance the hand. And similarly, for page 3, we're also not going to kick it out because we just referenced it. So this is good that we're keeping track of it. So now we would change its reference bit from a 1 to a 0, advance the hand, and now we have page 4. So whenever we have page 4, we go ahead, its reference bit is 0, so we can replace that with page 1. Yep.
So when we check the 3, why did the hand not point to the 3 afterwards?
Sorry, when we check the 3.
Like we did 1, 2, 3, 4, 5, 2, and then 3. So at 3, why was the hand still pointing towards the 2 and not the?
On references that are already in memory, you just update the reference bit, you don't touch the hand at all.
Oh, but so you actually check it buffer for 3, and if it is in there, you update and the hand will move?
Yeah, you only check like what the hand's pointing at whenever you know you have to swap in. So whenever it's not in memory.
So they will still do like so that hand doesn't actually.
For which one? Sorry.
So like if the 3 is in, so when we try to check for 3, something else will just check this entire buffer for the 3.
Yeah, so like there'd just be a reference bit associated with a page. So here, when we access page 3, all it would do is change the reference bit for page 3 from a 0 to a 1, and that's it. It's not going to monkey around with the hand or do anything because we're just keeping track. We're trying to approximate least recently used, so we're just keeping track whether or not it was used or not. So we just set one bit. Yep.
When we update, next slide. When we update, after we update, we should use the hand, right?
Yeah.
But everything else confusion.
Sorry? So
If you go to 2, and then you have to update 2.
So this is what it looks like after we swapped in 5. So here right before, this is like, we're looking at page 2, its reference bit is 0. We know this one's going to get swapped out. So when we swap it out, we swap in page 5, its reference bit is 1, and as part of putting it into memory, we just move the iterator 1. Because, yeah. No. No. So right here, after we insert page 5, the iterator points to the element after the 5. If it pointed to the 5, that would be kind of silly because next time we try to swap in something, it would try and replace the thing we just put in. So we wouldn't want to do that. That's why after we update it, after we put it in, we advance the hand 1. And then this, whenever we access page 2, it's already in memory. So we don't want to monkey around with the hand. That would just be too slow. All we want to do is is change 1 bit. So we'd only change 1 bit. So for the access for 2, it just changes its reference bit from a 0 to a 1. Yeah, when you find it, if it's in memory, all you do is set the reference bit to 1. Yeah.
When the second time we access the 2, why we move the hand?
When we access 2,
From the 5 to 2.
we didn't. So right here, this is what it looks like right after we inserted 5. This is before we know about 2. So we didn't, access to 2 didn't change the hand at all. So whenever we insert, we put the iterator 1 past whatever we just inserted. So the access to 2 didn't touch the hand at all. So the only thing the access to 2 did, so this is what it looks like after the access to 5. And then as soon as we touch 2, all we do is change the reference bit. So the reference bit goes from a 0 to a 1. Yep. And then for the access to 3, again, same thing. So 3 is already in memory. We don't want to monkey around with the hand at all, do any slow operations on every access. We want to make sure that whatever we do for each access is going to be really, really fast. Flipping a bit is pretty fast. So after we access 3, its reference bit is updated from a 0 to a 1, and now we access page 1, so now we have to swap something out. So this is where we would start monkeying with the hand. So the hand's currently pointing to something with the reference bit as 1, so we would just change 1 to a 0 and advance the hand. Now it's pointing at page 3, reference bit is 1, so we would change the 1 to a 0, advance the hand, and now we're pointing at something that we can replace. So, yeah.
So when you want to find something, you actually don't do it. You just create like a temporary thing to move through the top to see if you find it.
Well, whenever you need to replace something, the first element you look at is whatever the hand's currently pointing to.
Right. So every time you replace, or if you put a new thing in, that's where the hand will point to.
Yeah. Yeah, the whole monkeying with the iterator and using the hand only comes in when it's not in memory and you need to swap it in. Yeah.
How do you know what's actually in physical memory and whether or not, like how do you know what's actually there? That it's like you're not looking at the iterator. Like on a hit, how do you know if you have a hit or a miss? Because this algorithm only runs when you have a miss, right?
Yeah, this only runs whenever it's not in memory.
Right. So how do you check it? How do you know if it's in memory?
So that would be just part of the kernel that keeps track of, like it has to do the swapping so it knows what pages are where. So this would all be handled in the kernel. Okay, so now for access to 1, now we're pointing at page 4 here. Its reference bit is its reference bit is 0, so it is now gone. So we're going to swap in 4 with 1, and its reference bit would be 1, and we would update the hand to point to the next thing. So after we resolve the access to 1, this is what our this is what our clock would look like. So we'd be pointing at 5, and the reference bit would be 1 for page 5, 1 for page 1, and then page 2 and 3 have 0 for reference bits. So now the other accesses we're going to have an access to page 2, It's already in memory. All we do is update the reference bit from a 0 to a 1. And now for page 3, same thing. It's already in memory. We just update the reference bit from a 0 to a 1. Mm-hmm.
Are those arrows, not the hand, but are the arrows pointers?
Yeah.
So you are like, in worst case scenario, you are like following pointers around all of your physical pages to find.
Well, so the arrows around the clock are just to show that's a circular buffer, but it could just be an array or something like that. It could, yeah. This is mostly to illustrate so it looks like a clock and it's all cool and stuff.
I see. And does that mean each reference bit is actually on the page, or is there a separate piece of memory that just has the reference bit for all? Because you could, like, if you only have 10 physical pages, you could have like just like a register with the 10 bits, and you could do it that way too. Or like,
Yeah, all the pages would actually be used for something, so you couldn't just reserve a bit on a page.
okay, so these bits aren't actually stored on the page themselves.
Yeah, they'd be stored somewhere else. So they'd be, as part of the bookkeeping, they'd be stored somewhere else. So every page you have would have a bit associated with them, which is like, how many bits are in a page? A lot. So just 1 bit per page, which isn't that bad. So that doesn't add to storage as well, and make the bookkeeping just untenable. We'll see kind of the bit counting you can do when we get to file systems. So whatever we learn with file systems and keeping track of, essentially, file systems also keep track of blocks, which look a lot like pages. So we'll see some of that when we talk about file systems. So any questions about this? We'll see another example as well. But any questions so far? Okay, so yeah.
So you said they're not stored on the pages themselves, but that means the kernel has its own like page that it just keeps just for itself.
Yeah.
To have all these values on.
Yeah. Yeah, the kernel, if it used this algorithm, would have just like a reference table that it would keep track of all the bits. Okay, so if we write out all the page faults here for it, well, for the first access, we swapped in 1, then second one we swapped in 2, then 3, then 4. Then for page 5, we replaced it with 1. And again, this is, if you were actually doing this, you would write it while you had the clock, so it would make more sense. So for the access to 5, we replaced page 1. And then remember when we did accesses to page 2 and 3, since they're in memory, it would also update the reference bit. And then when we accessed page 1, that's when we had our miss. And we replaced it with we replaced page 4 with page 1. So, and then the next 2 accesses we had in memory. So if we count this, we had 6 page faults. Okay, so I guess for practice, so if it was 6, we can go ahead and check whatever the optimal was. Whoops. So if we had the same accesses, what would happen if we did the optimal strategy? So for the access to page 1, oops. What are we going to do? Yeah, so we're assuming that there is nothing in memory, so we would swap it in. So we would just swap in page 1, and then it's going to look the same thing. So for page 2, we would swap it in. I'm going to skip some steps. 1, 1, 2, 2, 3. So for our first 4 accesses, this is what it's going to look like. And it's always going to be pretty much the same. And now we have access to page 5. So it is not in memory. So if we are doing the optimal strategy, what should we kick out? I see a 4. Everyone agree with 4? So let's see. would it be a 4? So we're currently accessing page 5. Well, the optimal algorithm just looks in the future and replaces whatever page is not going to be used in the longest time. So between 1, 2, 3, and 4, it's not going to be 2, it's not going to be 3, and it's not going to be 1. Therefore, it's going to be 4. So we would swap out 4 with a 5, and that is another page, that's another page fault. Now, since we use the optimal, thankfully, whenever we access page 2, everything's already in memory. So we have a hit, and then when we access page 3, also going to be a hit, because again, we use the optimal thing. And then when we access page 1 again, then it is also going to be a hit. And then again, we access page 2, it's going to be a hit again. And then page 3 is also going to be a hit as well. So in this case, our optimal, we had a total of 5 page faults. So pretty good. So with clock, we did 6, and with optimal, it was 5. So let's go ahead and look at a bigger example and see how well we understood the clock. So here's our axes, and we'll do this using the clock. So I will draw one over here, and again, we'll just assume that there's only 4 pages in memory. So if I draw my little clock, it would look like 0, 0. So this is what it would look like initially. So now if I access page 1, what's going to happen? Yeah, so I put 1 in, so it is now in. So page 1 is in memory now, and I change its reference bit to 1. And what else should I do? Move the hand by 1. So I move the hand by 1, so that's what it looks like right after the access to the first page. So I just swap that into memory, so I will record that. So now we have a access to page 2. What's going to happen? Just put it in again and advance the hand. Right? Same story. So we put it in, its reference bit is a 1, we advance the hand, and now after that we have swapped it in. Now for the access to page 3, well, it's going to be the same thing again. So we swap it in, set its reference bit to 1, and then advance the hand. So now we swapped it in. It's going to look boring because for 4, it's going to do the exact same thing. So 2, 3. So the current hand's pointing at something with a 0. We're just going to put it in. We swap in page 4, set its reference bit to 1, and then go along, advance the hand. So now we swapped in page 4. So now what's going to happen when we access page 1? Yeah, so it's in memory. Do we have to do anything? Would we have to do anything if its reference bit was a 0? Yeah, you'd have to update to a 1, but in this case, it's already a 1, so I'm good. I can just enjoy this page hit. Now I'm going to access element 2. Element 2 is also in there. Its reference bit is already a 1. I don't have to bother to do anything again. So we have another hit. So now when we try to and access page 5. It is not there. What should I do? Yep.
You loop around the clock, change each bit into 1 until you find a 0 bit that you can swap to a 5.
Yeah, so I'm going to be looking, just advancing the iterator until I'm pointing at something that is a 0. If it's currently pointing to something with a reference bit as a 1, I change the 1 to a 0. So this is like when we go around the entire clock. So page 1 that it's currently pointing at, its reference bit was a 1, we would change it to a 0, and then we would advance the hand. Now, same story, we're going to change the 1 to a 0, and then advance the hand. Again, 1 to a 0, advance the hand, 1 to a 0, advance the hand. And now we're finally pointing at something, a page that has 0 for its reference bit. So in which case, we would choose to swap it out. So we've chosen to swap it out, so we put in page 5, set its reference bit to 1, and then we advance the hand when we're done. So now we swapped out page 1 with page 5. So now our memory, the pages in memory are 5, 2, 3, and 4. So now we will have an access to page 2. So that is in memory. Is there anything else I need to do? Yeah, change its reference bit from a 0 to a 1. So I did that. So now we're looking at the access to 3. It is also in memory. So I would have 5, 2, 3, 4. What do I need to do? Yeah, change the reference bit again. And I don't monkey with the hand or do anything slow. So now we have access to page 5. It is in memory, and its reference bit is already a 1, so we don't have to do anything. Similarly, for an access to page 2, its reference bit's already 1. We don't have to do anything. Now, we would have an access to page 1. So we have, oops, that looks ugly. So we have to pick something to get rid of. So currently the hand is pointing to something with a reference bit a 1. So we would change it to a 0 and advance the hand. Now, page 3, reference bit is also still 1, so we would change it from a 1 to a 0, and then advance the hand. Now we're pointing at something where the reference bit is 0, so we get rid of it. So we replace 4 with 1, and then set its reference bit to 1 and advance the hand. So now we replaced 4 with 1, 2. Which was kind of unlucky because we were actually using page, we just